Okay, in this video I'm going to continue with the double slit diffraction problem and actually calculate the difference in path length between the two beams of light that are coming from the two different slits. Let's say we have one slit here and one slit here. What's the difference between the path length of this beam of light and that beam of light? Now, even though they look parallel, remember they meet at the point of the distant screen. So of interest to us is, can we figure out how much further one will travel than the other? Alright, so parameters of significance include this angle theta here, which is going to be the same for both of them because they look, as I mentioned in the previous video, they look parallel. So it's going to be that angle theta and the distance between the two slits. So I'm going to use that information to try to figure out how much further does one beam of light travel than the other. Okay. So I'm going to draw a blow-up of this scene right here. So the blow-up will be right over down below right here. So here's my wall again. Here's one slit. Here's another slit. Here's my two beams of light, let's say, in this case. One's like this. The other's like this. Now, since the point is up here, somewhere up here in the distance, it is the lower beam, this one, that is going to travel further than the higher beam. So what is the distance further that it travels when reaching that distant point? Well, if we're assuming parallel rays of light, which is, again, it's an assumption, but it's not a bad one, when the distance here x is much greater than the distance d, then assumption of them being parallel is okay. But when they are, here's what we can do. We can take a right angle here and say that the greater distance that's traveled by the lower beam to reach this distant point over here is actually equal to this distance right here. So all we need to do is calculate the size of that distance there. Given that here's d, here's theta, and also here's theta too. Is it the same theta? Alright, so that's what we need to do. We can actually realize that this theta is the same as this theta because this angle here and this angle here make up a right angle, and so do this angle here and that angle there. Therefore, this angle here is theta, and that between that being theta and this being d gives us everything we need to know to figure out how much further this lower beam of light travels than the upper beam of light. New slide. Okay, so I'm going to redraw that situation right here. That's all I need to draw at the moment. I won't distract you with all the other pieces of information, but this is what I'm interested in finding, that length there. Here's my right angle. That's the hypotenuse, is the d. That's the theta. I'm interested in this side, which is also known, you can think of this as the opposite side, and it's a distance. D is in meters, so this opposite side is also a distance in meters or fractions of a meter. And we could say that sine of theta is equal to the opposite side over d. So the opposite side, or the difference in path length, which I'll call delta r, the difference in path length, is equal to d times the sine of theta. Okay, so that's really helpful to me. Okay, new slide. So when that difference in path length is equal to one wavelength, well, zero wavelengths I should say, one wavelength, two wavelengths, three wavelengths of light, etc., some integer number of wavelengths of light, which I'll call n, then the two beams of light interfere constructively. They build each other. However, when it's equal to half wavelength, or when that's the case, they interfere destructively. And you'll see a black dot on the screen. Okay, so it's pretty fascinating. Notice that as you change the angle of light coming from the two slits, you will affect whether the two beams of light interfere with each other constructively, in which case you'll see a bright light or a bright patch on your distant screen at a certain angle, or destructively, in which case you'll actually see a dark spot on the screen at some angle. Okay, I'm going to stop this video and then create another one where you'll actually do the final calculation of the relationship between the wavelength of light, the distance between the spots, and that's pretty much it in order to determine the spacing, the angular spacing between the bright and dark fringes on the screen.